Welcome back. In the previous video, we covered ordinary least square regression with gradient descent. Gradient descent being the method that we use to estimate our coefficient. So in this video, we're going to cover regularized method for regression. The basic idea of regularized method is that it tries to address some of the problems of ordinary least squares by imposing a penalty on the size of the coefficient. Now, we highlighted previously when it comes to ordinary least square or linear regression is that it is subject to outliers impact. Whenever you have any outliers, it actually shifts the coefficient quite substantially. Now, that's where the regularized methods such as ridge regression, lasso, as well as elastic net comes in. They each have a slightly different way of imposing or regularizing the so-called coefficient and imposing a penalty so that the coefficient is actually regularized, okay, or restricted is probably the other way to actually look at it. So the ridge regression, what it does is that it imposes a penalty term. Now, in a normal ordinary least square, this is what you see. This is the minimum of your estimates minus the actual y, okay, square. And this portion here is the actual penalty term. Now, in this part, it's trying to minimize the actual residual sum of squares. Okay, so alpha greater than 0 is a complexity parameter. As another term of it is called alpha. That controls the amount of shrinkage. The larger the alpha, the greater the amount of shrinkage, and thus the coefficient become more robust to collinearity. Collinearity meaning the so-called correlation between the actual independent variables itself. Now, ridge regression is an L2 penalized model. It adds the sums of squares of the weight to the least square cost function. So that's really this portion here. Now, this part here is directly from the scikit-learn library. It's really to illustrate a couple of very basic, simple things. It shows the effects of collinearity in the coefficient of an estimator. Now, ridge regression is the estimator used in this example. Each color here represents a single feature of the coefficient vector. Now, this feature is displayed as a function of the regularization parameters. This example basically shows the usefulness of applying ridge regression to a highly ill-conditioned matrices, which is this Hilbert matrix here. For such matrix, a slight change in the target variable can cause huge variation in the calculated weights. In such case, it's useful to use certain amount of regularization, such as alpha, to reduce the variation or the noise. So we'll just run this. I won't go into too much explanation of it. Now, basically, as alpha increases, it increases the so-called regularization. Okay, so when alpha is closer to 0, it is closer to basically a normal linear regression or ordinary least square. Okay, so around here, 10 to the minus of 10, basically it's no penalty. Okay, basically no regularization being imposed here. And you can see that the so-called weight just basically explode, okay, and it's all over the place. And as you actually start to increase alpha, notice that this is 10 to the minus 10, 10 to the minus 9. So as alpha increases this way, right, as alpha increase, the so-called regularization increase, the so-called coefficient start to stabilize and all converge to 0. Okay, so that's really the weight here. Now, this part here, if you understand how that works, that's great. If not, don't worry about it. Okay, that's really directly from the scikit-learn library. What I want to do now is to actually walk through with you a little bit more about lasso and also elastic, the other two so-called regularization method, before I show you some example, okay, code example that makes it easier to develop the intuition. A lasso regression is basically a linear model that estimates sparse coefficients. Now, mathematically, it consists of a linear model trained with L1 prior as a regularization. The objective function looks like this. This portion here may look very similar to the previous part, and basically it is, with some slight variation. The difference here to the previous ridge regression is this portion here. Okay, the lasso estimates that solve the minimalization of the least square penalty with alpha times the weight added, where alpha is a constant and W absolute 1 is the L1 norm of the parameter vector. Basically, is actually the L1 regularization. Okay, L2 here is basically square. Okay, so that's where the weight is square. L1 basically is the absolute term itself only. Now, ElastiNet is trained with L1 and as well as L2 prior as a regularization. Now, this combination allows for learning a sparse model where a few of the weights are non-zero like lasso, while still maintain the regularization properties of ridge. Okay. Now, just continue on the explanation of ElastiNet. Basically, it's actually a combination of both lasso and ridge. Now, lasso really is this portion here. As you can see, is actually duplicated here, and the W square, the L2, all right, regularization is this portion, and this is the portion that is exactly the same as ridge regression. These alpha and alpha 1 minus theta, 1 minus rho here, divided by 2, that's really this portion and this portion. So this is just the weightage of it. I wouldn't put too much weight and attention to that part. It's the key thing to pay attention to is this W1 and this W2. This is the L1 regularization. This is the L2 regularization. ElastiNet is useful when there are multiple features which are highly correlated with one another. Lasso is likely to pick up one of these at random, while ElastiNet is likely to pick up both. Now, the practical advantage of trading off between lasso and ridge is it allows ElastiNet to inherit some more ridge stability under rotation. So basically, the objective function to minimize in this case is really these two here. So just to summarize, the building block really is ridge as well as lasso. Now, the beauty with lasso is that if certain so-called independent variable it finds is actually correlated, it will just drop it off. Okay, let's just say x2 and x4 is correlated. What it will do is that it will likely drop either x2 or x4. Whereas ridge is different. Ridge will actually still give it a weight, albeit regularized or with a penalty, okay, imposed. Whereas linear regression will not pick up the collinearity at all. And what you're likely to get is that you will have exploding coefficient for these two, but at the opposite end. For the x2 and x4 that I was talking about, one might be plus 10, whereas x4 might be minus 50. So really, really large coefficient to compensate for each other. That's where you're likely to see when it comes into effect, when you actually have the collinearity in effect. So enough of theory. Let's look at the code just so that it's easier to grasp. Now let's look at outliers impact. So what I really have done here, so the first cell here is just import some basic libraries that we need, and we're running a linear regression model as we did before. I set the seed to 42 so that you can replicate this. I set the samples is 100. I've instantiated the linear regression. This is the so-called generated function here. So let's just move this here so that it's easier. You don't get confused with the actual code itself. So let's look at this formula and just try to understand it a little bit. So we are generating 100 random numbers, normal random numbers, and multiply it by 10, so basically magnified. And the slope of this random number is 0.5, so it's half, plus 2 times, this is really the noise term here. Okay, so, and we instantiate the linear regression, we fit it, and we run prediction on the actual random number, which is the x, or the independent variable, or the predictor variable. So we plot that out, plot the scattergram diagram of the x and also the y. We call RNG random number and y generated number, and we plot the actual model, the so-called x again, and also the predict that we actually ran here, and we print the coefficient. Now the coefficient here should really be 0.5. Okay, so this is just a basic model. There's no outliers here, so it's just really to you can see that the linear regression recovered this pretty well. 0.5 was the actual number. With only 100 samples, it recovers it pretty well. All right, so okay, what we've done here, okay, in this in the sense of this cell here, is that we try to find the index where the RNG, or the random number, is maximum, which is really this is the largest number in terms of the X. And what we did is that we changed the Y, the corresponding Y right now is around 9, 8, and we impose or replace it with 200, so really large outlier. Okay, so let's just plot it once again, and this time around we're running a linear regression. O here stands for with outlier. We're running a linear regression, but we just normalize the so-called inputs. Okay, and so random number, again the same random number generated. Y really is the Y from earlier, and also running the model predicted, plot the scatter diagram, and then plot our model once again, so and print the coefficient. Okay, here you see this time around the effect of the outlier. Notice this is the outlier that we replace. Okay, and you can see the linear regression being tilted quite substantially, and it wasn't able to recover the coefficient from before. The coefficient from before was 0.5. Because of that outlier, it basically dragged the whole equation upwards. And there's really only one outlier. Can you imagine if there's a few more? Okay, let's look at ridge. All right, remember this is a regularization technique. Okay, so let's see what is the effect here. We're plotting as usual what we had before, the figure, the scatter diagram, and this is our model. Okay, this line really is just setting the ridge, and also setting the alpha is equal to 1, which is quite large, and then we're fitting the model here, and finally we run the prediction on the X, or the independent variable. We plot the scatter diagram, which is already done here, so let me just delete that. We don't need to repeat that. Okay, so let me just tidy the cell so that it's easier to see the okay, so we set the figure to that size, we plot the scatter diagram, and we plot a straight line of the ridge regression model. Okay, this is what's predicted, so this is our Y, and we plonk it here, and we print the actual coefficient itself. So let's run this, and you can see that the ridge is substantially better at recovering the original coefficient, which is 0.5, and this is 0.46. It basically ignore, all right, the you know, it actually, although it still gave some weight to it, but it actually you know, is not as badly affected as the linear regression, which is substantially being affected. So let's look at lasso. We are basically repeating the whole exercise. Again, we don't need this. Let me just move this down. And okay, so this is lasso, setting the alpha is to 0.4. There's a bit of hyperparameter tuning here. I've already preset it for you. I'll give you as an exercise to try that out a bit later. Again, fit the model, predict the model. By now you can see that the actual steps are pretty straightforward. Plot the figure, set the figure size to 10.8, scatter diagram, plot our model, and print the coefficient. Okay, as again, you can see that with lasso, it is able to actually pretty much and quite closely recover the 0.5 slope. Again, it basically is not affected by the single outlier at all. And finally, we're looking at the elastic net. Okay, and again, same model. We don't need this line once again. Okay, so we just need to plot the figure, plot the actual original data, plot our model and its prediction, and print the coefficient. Again, with elastic net, 0.45, which is pretty good. Okay, 0.45, 0.48, and 0.46. So in this case, lasso performed the best, followed by ridge, and finally followed by elastic net regression. Okay, just to summarize, this is a question in Stack Exchange. So by now you probably are thinking, oh, when do I use lasso? When do I use ridge? Or when do I use elastic net? Not elastin, elastic net. Well, ridge regression can zero out all the coefficients. So you either ended up including all of the coefficients in the model or none of them. Okay, so that's really everything is contained. All of the so-called independent variables is actually included in your models. It's just the actual coefficient estimates is won't be zero. Okay, lasso does both parameter shrinkage, okay, and variable selection automatically for you, so you don't have to worry about that. So some of the parameters or the variable, it will just select or remove it or give it a zero weighting altogether. Now, if some of your covariates are highly correlated, you may want to look at the elastic net instead of lasso. If you want to look at more references, you can look at the lasso page. And the last one really is actually more of a book that's uploaded. And feel free to actually have a look at it. It's actually Stanford, one of the professor wrote this book. It's called Elements of Statistical Learning. It's really a very comprehensive book. I've read through it. I can't remember how many pages now. I think it's 300-400 pages. It's basically provided online for free, so feel free to actually look into it. Now, before we close this off, I'd like you to pause the video, all right? And this time around, okay, try to actually do this simple exercise. Change the y to 100, okay? See if you can do this same exercise. Find the smallest number of the axis, which is the RNG here, which is this one here, and put a really negative number like -200, and run the whole exercise again. And just so that you actually develop some intuition, try a smaller alpha for ridge, a different number for lasso, and again another different number for elastic net. So try that out, okay? Give yourself a chance to play with the model. That's really the best way to develop the intuition. And when you've done that, continue with the video. When we come back, I will summarize the lesson itself. How did that go? I hope you have found the exercise useful. Really, the whole exercise here is for you to actually develop an intuition. So let's just say I mentioned before, now instead of finding the max, we find the min. Instead of 200, we change it to -200, and basically run the whole exercise once again. And you can see that the coefficient is far worse now, 1.5. We run the ridge regression. If we change it to 0.5, see what happened. See, notice that it's not doing so well now. It's 1.00. So this is where you might actually have to increase the alpha in order to actually compensate for that. So if you use 0.4 again, notice that lasso is also impacted, but not as bad as the linear regression, elastic net. Let's just say we leave everything the same. Okay, elastic net did the best at 0.74 in this situation. So there's no one size fit all. Sometimes ridge does better, sometimes lasso better, sometimes elastic net. So that's really the morale of the story, is that two things. One is that outlier really have a great impact on your model. Two is that you do need to tune your algorithm to find what works best. All right, so with that, I'm going to end this video. I hope you found that useful. In the next video, we're going to go into polynomial regression.